we have discussed a very simple form of processor design called single cycle design, and in the last lecture we ended by making some observation about such a design. These observations were about its performance and inability to do certain kind of instructions. So, today we will introduce another type of approach called multi-cycle design, which tries to overcome these problems. This is the overall lecture plan, and today we will start by repeating those problems, reobserving those problems which are related to single cycle data path. We will look at how we analyze the delays and what was the difficulty which was noticed. We will see how clock period can be improved, how clock could be speeded up by using multi-cycle design. We will also look at this as a way of improving the resource utilization. The resources are the main hardware components we have even in our data path, and what basically we will do is we will try to share these components such as memories and ALU, and to facilitate that we would need to introduce some more components, but of a lower cost generally. These are registers and multiplexers. So, this is the data path which was designed in the previous lectures, where every instruction is completed in a single cycle. So, all activities begin with a new address in PC, and the cycle ends by updating the PC value as well as updating the state of the whole processor in register file and memory. So, these are the three problems which we had noticed, that the slowest instruction pulls down the clock frequency. So, if there is a wide disparity in the timings of various instructions, then the whole set of instruction will be running as slow as the slowest instruction. So, that is a difficulty with such a design approach. And secondly, resource utilization is poor. Apart from having a full fledged ALU, we had to use two adders, and we had to keep the instruction memory and data memory separate, because in that type of design it is not possible to work with single memory from where you fetch an instruction and then later on fetch data also. So, that will not work out. Also, I hinted upon some kind of instructions which cannot be realized by this type of approach. So, we will focus today on first two issues. Just to recall that we had analyzed the performance by taking the delays of individual components. Some simple ones were assigned 0 delay, and others had some significant delay denoted by T plus TA and so on. These symbols are denoting the delays of individual components, and for each instruction or a group of instruction we enumerated various paths from storage element to storage element through which the data has to flow in the instruction, and identified the possible expressions which would decide the overall clock period. So, this was the final expression we had. The one at the bottom is in a simplified form, and it would be noticed that the largest of these sub expressions will actually decide the clock period. To illustrate this further, let us look at some values. So, again I am not putting these values in numeric sense, but trying to depict it pictorially. So, the horizontal axis here is the time axis, and for each instruction I am trying to show the delays which are involved in the flow of information along the data path. So, for R class instruction there is delay involved in fetching the instruction, fetching the operand from register file, then doing the arithmetic operation, and finally storing the result in register file, and so on. For each instruction I have indicated the possible paths which may dictate the clock period. So, I have taken nearly equal values for all these terms, except that there are slight differences. Ti and Tm I have taken same, and in fact T plus is also same. Ta is slightly less than that, and Tr is even little less than that. So, from first three cases I have dropped the T plus term, okay, because that is invariably that is less than all these, and we do not really need to look at that. So, now you can very clearly see that LW with this kind of values, LW will dominate and dictate the clock period. So, clock period would be from this point to this point. Remember that horizontal axis is the time axis, I am showing along the timeline. And but once clock period is fixed, all instructions are taking same time, and you could see so much of dead time in other instruction, in R class, in SW, in BEQ, and most in J. Okay. So, now when we introduce multi-cycle design, basically what we try to do is divide execution of instruction into multiple cycles. So, we need to decide what gets done in first cycle, what gets done in second cycle, and so on, and there are lots of choices. So, we will take one simple choice here, which tries to do one major action in one clock cycle. Okay. This is only one of the possibilities, and what it means is that now looking at each individual times, we take max of these and take that as a clock period. So, in this case Ti, Tm or T plus all are equal and the largest among all. So, that decides the clock period. The R class instructions now get done in 4 clocks, LW in 5, SW in 4, BEQ in 3 and J in 1, right. So, there are still small dead times because of inequality, because all these times are not exactly equal, there is some differences, but you would notice that the overall improvement in performance will be there, because the overall wastage in time is much smaller. One more thing you must notice is that the total time LW takes now is more than what it was taking earlier. Okay. Earlier it was taking 1 clock which was from here to here, now it is taking 5 clocks which goes from here to here. So, because there is some wastage of time here also, but on the whole everything put together, this approach would still give you better performance or save time. Now, things look quite okay here, quite good here, because these different time parameters are nearly balanced. Okay. I deliberately took these values which are only slightly differing from each other, and therefore, the wastage you see is very little. But suppose there was a vast disparity in these times. So, we will be again having a problem situation. For example, suppose for some reason the adders which we had for address calculation for branch and jump instruction, sorry not jump, branch instruction and doing PC plus 4, they were pretty slow. So, let us say T plus becomes the bottleneck, and this will hold up the clock. So, now clock will get dictated by this time, right, and we will still follow the same approach. R instructions take 4 cycle, LW 5 cycle, SW 4, BEQ 3 and J single cycle. But now notice that the clock period is larger, and it has to be sufficient to accommodate each of these, any of these individual activity. So, T plus is dominating, and you would notice that now even these instructions, although they are taking 4 cycles, but they are taking longer than what they were taking in the single cycle approach. Of course, LW was in any case taking longer than single cycle, SW is also taking longer than single cycle, and in BEQ there is a little bit of saving, there is of course still significant saving in jump instruction, but there are very few jumps anyway in the whole program. Okay. So, if you add the cycles per instruction CPI of all these, now R has CPI of 4, LW has 5 and so on. So, we know the CPI of individual instruction or class of instruction, and we have seen how we can calculate average CPI depending upon the frequency of occurrence of certain kind of instruction in a program, you can find an average. So, the total time a program would take could in fact here be larger than what it would take in a single cycle case. So, if there is an imbalance of this nature, then this approach, the way we have implemented multiple cycle design, could be counterproductive. So, what can be done in such a case? We have to do something so that there is balance. Okay, what we are doing in a clock cycle is uniformly true, uniformly same. That means we identify the activity to be performed within a clock cycle which is generally balanced. Okay. So, it should not happen that for example, here in this clock cycle we are doing little, very little, and wasting a lot of time, whereas this cycle here is packed. Okay. So, that is the unbalance. How to balance? Possibilities are that you can have multiple actions in a period. Okay. If there are two, let us say 2 actions which are taking very little time, you can do 2 in a clock. Earlier we were doing everything in a single clock. Okay. So, that kind of idea could still be retained. We need not say that one action in one clock cycle, although that is the simplest thing, but this may not be always very beneficial. Alternatively, or in addition to this, you could have multiple periods for an action. Okay. For example, it is not necessary that t plus, if it is slow, has to be done, this action has to be done within a single clock. So, you might do everything else in a single clock, but maybe reserve 2 clocks for this, right. So, you might still have an overall better performance. So, now once you bring this into picture, the number of possibilities become very large, and it is not a very straightforward solution, but the point here is that one could find a suitable clock period, so that the dead times or the wastage of time which is due to quantization of time by clock is minimized. So, we will not go into further details of that. We will just assume that we have identified the major actions for each instruction, and each can be put in one clock cycle. So, we will follow that approach, keeping at back of our mind that if there is a problem, this is the direction in which we need to look into. Okay. The second issue was improving the resource utilization. Can we eliminate 2 adders? Can we just manage with a single ALU? That is one question. In general, how do we share resources across cycles? Okay. You are using adder in one cycle to do something, in another cycle you can do something else with the same adder. So, the solution lies in having the results of one operation stored at the end of a cycle in some register. Okay. You recall 2 designs of multiplier we discussed, 2 different types of design. One was array multiplier, where we had a cascade of adders with no storage in between, and the partial sum flows through all those adders. Okay. So, now as data flows through those, you can notice that each one is not getting fully utilized. Each would be active when signals are propagating through that only part of the duration. On the other hand, the sequential multiplier we had, we did something with the adder, stored the results in register, and reuse that adder again. Okay. So, the key thing is that between 2 usages you have to store one result. Okay. So, you do something, store the result, and then the resource adder in this case is free to do the next operation. So, same idea we will apply here, and the 3 key resources we will keep in mind is register file, okay, ALU, which will do all arithmetic and logical operations now, and the 2 memories will be clubbed into a single memory. Okay. It will store program as well as data. So, let us take this as a starting point, which is a single cycle design, and in this we will see what changes are required if we have to share these resources, and we know that we are going to do a multi-cycle design. So, each major action would be done in a separate clock cycle. So, firstly let us merge instruction memory and the data memory, okay. Replace both these by a single memory. So, we remove these and replace them with a single block which is doing read as well as write, and I have placed it here in where program memory was kept, but what we will do is we will route its inputs and outputs back to the same memory. So, that means the ALU which was supplying the address, this will go back and supply an alternative address. This was the data input, this will go back to this point, and the data which is being read will actually now come out here. Okay. So, these inputs and outputs which were connected to these will now be rerouted and brought back to this particular block. So, first of all, this output of ALU, which is the address for memory, is connected back. Now, we are bringing a conflict here, but we know how to resolve that. We will introduce a multiplexer here to take care of this, but that is a problem we will tackle later. So, first of all, let us bring all connections here. I have taken care of address input. Next, the data input which is going here will be now brought to this. So, I have removed the old connection and it gets connected at this point. Similarly, the data which is coming out of memory and was eventually through this multiplexer going to register file will now come from this. So, that is removed, and this is okay. I think that is, yeah, it is connected here. Let me see it again. So, the output, old output of the memory is removed, and the new one will get connected into this. So, it comes out of this and gets connected. Again, we are bringing in a conflict here. We know that the data needs to be brought from ALU or from memory, okay, for load instruction and for arithmetic instructions. So, this is a conflict point we will resolve with a multiplexer again, and what we will do is, for the moment we will remove this multiplexer and reorganize it here later on. Okay. So, output of ALU is directly connected here for the moment, but we know that a multiplexer is required at this point. So, we have gotten rid of one extra memory. Now, gradually we will also collapse the two adders onto this ALU. So, first let me make space, let me just shift things around, so that there is space for carrying out interconnection. It is just same thing with thing moved little apart, and we will first eliminate this adder and then eliminate that adder, and same thing will be done. Remove this and just route the interconnections onto this. So, we remove that adder. It was getting two inputs, PC and 4. So, the input coming from PC is brought in to this point of the ALU. Okay. So, this is a new connection, and the second operand 4 will be brought to this multiplexer. Okay. The output of this adder which was here was eventually going through this multiplexer to be stored back into PC. Okay. So, that we will have to tap from this point now. So, we remove that connection from top and take a connection from here. Okay. Now, we have still something hanging here. This was PC plus 4, which was being used for offset addition here and generating jump address here. So, this will now come from PC, because we are assuming that you do PC plus 4 in one cycle, the result goes back to PC. Okay. So, the input to this is not taken from here, we take the value, since it is a multi cycle design, PC plus 4 would be done in a particular cycle, and that value will be put back into PC, because remember that we are going to put all values into some storage element in some register at the end of the cycle. So, that resource which computed that becomes free. Okay. So, this input here will come from PC now. I simply make that connection there. So, we have taken care of removing the first adder. Now, we eliminate the second adder, this one will be moved away, and its inputs again brought to the same ALU. Okay. So, we have this output from PC, which is already coming to this. So, that actually will not bother us, that is already there. The second operand is coming from the offset eventually, and that would be brought to this multiplexer. The output from here will have to go to this multiplexer. Okay. Yeah. So, this second output, second input to the old adder is removed from there and is connected here. Then we simply get rid of the first input, because that is already taken care of, and the output I make some space first for that, and then connect the output. So, this is now one might question actually that sorry, that why is it that we are still having two inputs to this, they seem to be coming from the same point, but actually it may be a little difficult for you to see. What will actually happen is that although this value which is actually supposed to go to PC, as this is a PC plus 4 value which is coming on this line, it is meant to go to PC immediately, but the other thing which is coming here for after offset addition is meant to again go to PC, but this is after comparison has been done in this ALU of the two registers, and this may go, may not go. So, what will happen is that first this value will get immediately stored in another register here. Okay. Before we do it, before we take further decision of sending elsewhere. So, at the moment I am keeping these two both which look identical right now, but one will come immediately from the output of ALU, one will come from a register which is following ALU. So, that distinction will show up later. So, at this point you just take it like this, that we are simply retaining. What if one was following this kind of design process, you might actually if you are not able to see that, you may eliminate one of these. Okay. But does not matter, one if you need one later again separate one, then you can bring it back into the picture, but I am just following this approach. Okay. Now, we need to introduce registers at various places. So, that output of every resource is stored in register, and I simply make some space for that and gradually introduce the registers. So, which are the points where we need to introduce registers? What we are reading from the memory needs to be kept in a register. We are reading two things, the instruction, and we are also reading the data which needs to go to register file eventually. So, two registers will be required here, which store, one will store instruction, one will store the data. Then you are reading operands from register file, they will be kept in small individual registers here. The output of ALU will be kept in another register here. So, these are the places where we need to put registers. So, we place one register here, we call it IR or the instruction register. One register we place here, we call it DR or the data register. Okay. So, both are carrying information brought from the memory. Then A register holds the first operand and B register holds the second operand, which come out of the register file. Then there is a register which we call RES or the result, which comes out of the ALU, and here I have made the distinction that PC plus 4 value is immediately going to the PC from ALU output. Okay. So, it is getting stored, but getting stored in this PC, whereas the other things, what else ALU is doing? ALU is doing normal addition, subtraction and or SLT operations. So, that data will get stored in this register before it goes to register file, and also the memory address which is being calculated for load store instruction will be resting in this here before it goes to the memory. And also for branch instruction, the next instruction address which I calculate by adding offset will sit in this register before I make a choice here whether to take PC plus 4 or PC plus 4 plus offset. Okay. So, that is the purpose this register will serve. So, now the last thing which remains is to introduce the multiplexers. Okay. And we will at some places we will require fresh multiplexer, somewhere we will simply do a rearrangement, okay, maybe enhance the size or restructure the multiplexer inputs. So, we have multiplexer already there which are feeding the program counter. Okay. What I will do is I will just collapse them into a 3 input multiplexer, 3 input 1 output multiplexer, which appears simpler, and physically just bring it out here. So, introduce a new multiplexer here, but I will eliminate the old ones. So, this has 3 inputs, one input comes from RES register, one comes from ALU directly, and one comes from this jump address. So, those 3 are brought in here. The output of this is going to feed the PC. So, first I switch the output, okay. Then one input comes from register result, one input comes from ALU, and the third input comes from jump address, and I have gotten rid of the earlier multiplexer. So, you can see it again. So, this is one connection, this is second connection, this is third, and this is the fourth. So, one output and 3 inputs. So, they are all rearranged. Okay. Next we look at the multiplexer which is taking care of the first input of ALU. Okay, ALU has 2 inputs now. The first input comes from either A, register A, or it comes from PC from here. So, simply I need to introduce a multiplexer here and connect these 2 inputs to that multiplexer. So, this is a 2 input multiplexer, one input comes from PC, another is already there shown from register A. Okay. Then this multiplexer which is feeding second input of the ALU now has 4 inputs: B, B register, the constant 4, this offset which is used for load store instructions for calculating the address. Okay. It is the offset in the instruction with sign extension. For branch instruction, we need to do a shift also, we need to do sign extension followed by a shift. So, these are two separate values and there are total of 4 possibilities. We need to have a bigger multiplexer here now. Okay, so, place a bigger multiplexer and simply connect these signals properly. Okay. So, we would need to see, we will need to worry about the control of these multiplexers. Okay. What control value, control input is required for different instructions. So, that we will analyze later in the usual manner. Okay. Then we move our attention to this area where we have data coming from DR or from RES that needs to be multiplexed before we feed into register file. So, just move that wire at the bottom. So, this one to make some space here where I will place the multiplexer. So, this is one input from DR. The output is properly connected and this signal coming from result is actually extended, brought to this. So, now this is taken care of. Finally, I need to put a multiplexer at that point. So, here we have address, there are two address sources, PC for fetching the instruction and this RES where load store address would be calculated and kept. This is another input. So, it will be simpler to just extend this line here and I will remove this line which is coming from top. Same thing, I just put it more neatly from the bottom. Okay. All right. So, now this is complete design of the data path for multi-cycle. For basically more effort was there to ensure that resources are properly shared. For that we need to collapse multiple components onto the same thing, and with the help of multiplexer we are able to feed different inputs to those resources at different times, and then registers were introduced to break the time interval. So, time interval gets broken into multiple clock cycles, and now the paths which need to be considered for delay analysis are much shorter path. So, for example, you can take paths going from one storage element to other storage element. When you are fetching instruction, it is this path PC to IR, or there are path from IR to A or IR to B, okay, or from DR to register file write, okay, and similarly path from A and B through ALU to result register, and so on. So, main sources of delay are these three components: memory, register file and ALU, and if these three are roughly balanced, then this will work very nicely. Okay, so that is complete design. We will look at the control part in the next lecture. I will just rearrange this diagram to make redraw this little neater. Okay. So, we will go into details of control signals. Basically, now we have lots of multiplexers. We have 1, 2, 3, 4, 5, 6 multiplexers there which require control, and multiplexers like this one will require 2 bits to control them. Apart from that, we have the usual control requirements for memory, register file and ALU, we also need to now look at these registers, in which cycle we load these registers and which cycle we do not. Okay. So, for example, if you take let us say add instruction, after the first cycle IR gets loaded, after the second cycle A and B get loaded, after the third cycle RES gets loaded, and then in the fourth cycle this RF gets the value written into it. Okay. Also, we will typically load PC with the new value PC plus 4 at the end of first cycle itself. If it is a branch instruction and branch has to be taken, that we will override that PC plus 4 value in the PC by a different value, and similarly in jump we will write something else in that. So, even PC will require a control. Okay. In every cycle we need to determine whether a new value goes into this or does not go, because there is no register which is now loading a new value in every cycle. So, this needs to be taken care of, and the number of control signals therefore is quite large. We have these 6 multiplexers, okay, out of which 2 require 2-bit input. So, total of 8 control signals we require just for multiplexers. We have 2 for memory, 1 bit for RF and 3 bits for ALU. So, this is another 6 bits, okay, and we have 1, 2, 3, 4, 5 and 6 registers. So, 1 control signal for each of these registers. So, there is a large number of control signals which are required, and also the control would be different in the sense that in every cycle there is a different set of control. Okay. So, the control will no longer be a simply combinational box, it will be a sequential machine which goes through a set of cycles, 4 cycle, 5 cycle or 3 cycle depending upon what instruction is, and in each cycle it tries to control things differently. So, the design is more involved in that sense, and that is the reason the single cycle design was considered first, being the most simple design. So, in summary, we have moved over from single cycle design to multi cycle design. We have compared their performance. Okay. We basically it gives you better performance, and by resource sharing it tends to reduce the cost. But now we must notice that there is a trade off. Okay. Although we are trying to gain both in time and in cost, somewhere there are losses also, and we have to be careful that losses do not overshadow the gains. So, for example, in performance improvement, if the quantization is too coarse and there is imbalance on the values of timings for different individual actions, then on one hand we might gain, but on the other hand we might lose all the gain, simply because there is a imbalance. Similarly, for while resource sharing, we have eliminated those adders and we have eliminated one memory, but we have incurred extra cost in terms of registers and multiplexers. Okay. So, you are sharing, but there is an overhead of sharing, and we have to be little more careful in our calculation and ensure that the overhead does not overshadow the gain. So, finally, just to close, we had a design where data path conceptually is simple in terms of the key resources, just one ALU, one memory and one register file, but there are registers and multiplexer which glue these all together. So, next we will look at the issue of control design for such a data path. Thank you.